Okay, let's do some more practice here. Example 2. So this is similar to the other ones that we did, where I have x in this instance is now equal to 4 cosine 2 pi t. Y is equal to 4 sine of 2 pi t, where 0 is less than or equal to t, which is less than or equal to 1. All right, so if I'm going to graph these parametric equations, I know that I'm going from 0 to 1. So that is my starting and my stopping. When I'm making my chart, oops, that's not helpful. I have t, x, and y still, but I'm breaking it up. So 0, I'm going to go with 1/4, 1/2, 3/4, and 1, because you want to be able to break that up enough in order to see what it is that you're doing. So plug it in. X is equal to 4 times a cosine of 2 pi times 0. So if I'm looking at this, what is a cosine of 2 pi times 0, which is this inside function? Yeah, so the cosine of 0 is 1. 4 times 1 is 4. You see that? Y is equal to 4 times the sine of 2 pi times 0. So the sine of 0 is 0. 0 times 4, still 0. All right. X is equal to 4 times the cosine here of 2 pi divided by 4. So 2 pi divided by 4 is pi over 2. So that cosine is 0. Y is equal to 4 times the sine of 2 pi over 4. So the sine of pi over 2 is 1. Then times 4 gives me 4. Do you see how this is shaken out? 4 times the cosine of 2 pi divided by 2. So the cosine of pi is -1, giving me -4. I'm not going to write all these out, so you get this, right? So the sine of pi is 0. X is equal to 4 times the cosine of 2 pi times 3/4. So you can reduce this here and say, oops, 2 goes into 4 2 times. So it's a 3 pi over 2, which I'm sure we all guessed, right? So at 3 pi over 2, cosine is 0. Sine is -1, so it gives us that -4. Then back to 1. X is equal to 4, the cosine of 2 pi, because 2 pi times 1, that's going to give me 4. And then we know the sine of 2 pi is 0. Okay. Awesome. Now, let's graph it. Remember, we are starting and stopping, and I'm heading it up here to 4. So let's make a nice big graph. So 1, 2, 3, 4. 1, 2, 3, 4. And 4. Now, I'm at 4, 0 here with my graph. I am then at 0, 4, -4, 0, 0, -4, and then back here to 4, 0. So I know that we're going to start here, and I'm going around the circle. Not awesome, but you see what's happening. You always need to put your orientation on there. So positive orientation in this instance is going to be in that counterclockwise scenario. All right, because counterclockwise, I'm starting here at 0 and then I'm swinging it around. And it just goes with how this increases, like how your points go here. As you go down that line, as t increases, your parameter increases, and that's the direction. That's what is considered positive orientation, the direction that your parameter increases, right? It doesn't have to go up, doesn't have to go down. And this time, It is counterclockwise is that direction. All right. So I want you to think about one other thing here real quick. So this is a circle, right? Obviously. So let's think circle for a second. Think back to what we know about circles. This is our generic form of a circle. X squared plus y squared is equal to r squared. This puts my origin at 0, right? Because x, so our actual circle is x minus h squared plus y minus k squared is equal to r squared, right? Where my center is hk and my radius of the circle is r. So if you didn't know that, there it is. And it's literally just that easy of a formula. So it's not anything fancy. This is just center radius form for a circle. Well, if my h and my k are both 0, then there's nothing here next to the y and the x to add or subtract. So it's just, this is a circle centered at the origin. And then I have my radius. All right. Okay. So let's go with what we have right here. My x is equivalent to 4 cosine 2 pi t, right? My y is sine. So in place of x, I'm going to write 4 cosine 2 pi, and I'm going to write theta in here. So I've got this squared plus my y is squared is equal to r squared. All right. So if I have this x value here and this y value, then square those things. I've got 16 cosine squared of 2 pi theta plus 16 sine squared of 2 pi theta. This is equal to r squared. Well, what do you know here? There's a 16 in common. We could totally factor that out. Good. Cosine squared. I'm going to make this a bracket. 2 pi theta. I'm going to make this bigger. Plus sine squared of 2 pi theta. Now what are you seeing? Maybe you saw it on the last step too, right? Cosine squared plus sine squared. What is that? 1, baby. This is your Pythagorean identity making that 1. So I really have 16 here is equal to r squared. So r is 4. What did we notice over here about this circle? My radius was 4 and I'm centered around the origin. So this form here is what we have this set up. This number in front is the same thing that we're looking at for my radius, right? Okay. Now, we're going to take this information and then we're going to come up with our generic equations for a parametric circle. So check it out. Parametric equations for a circle. When you have a cosine typically here is your x's, right? When you think about unit circle, cosine is your x, sine is your y. So that's the same thing that we're going to be looking at here with our parametric. I'm going to make this big again. Sorry for all the back and forth. So x is equal to a cosine bt. Y is equal to a sine of bt. All right? If I'm looking at this in terms of my circle, if this inside is greater than 0, then I'm going to be going counterclockwise. Oh, I do not know what I just did. Try again. If b is less than 0, aka negative, then we're going clockwise. Now let's think about that for just 2 seconds. Think about your unit circle. If I have a positive, so this is an angle measurement, right? If you have a positive angle measurement on your unit circle, then you're going in that counterclockwise direction with those positive angles. If I have a negative angle measurement on your unit circle, you're going in that negative angle direction, right? So this just totally connects. This is not brand new information. Yes, we're looking at this in terms of parameters, but it's what we already know. All right, we're taking previous information and just connecting it and just working these out a little bit different here with parameters. You got this, right? You have got this. You know, cosine already goes with the x, sine already goes with the y, clockwise positive, counterclockwise negative angles. Oh my gosh, I said it the wrong way. Counterclockwise positive angles, clockwise negative angles. Whoo-wee. That's a little bit of a tongue tie there. All right, so also, if I have x squared plus y squared, that's equal to r squared, right? Well, I'm going to put a because that goes with the formula better. So x squared plus y squared is equal to a squared. This is a circle centered at the origin. Right? Where r is equal to the absolute value of a. So that's that radius that we were talking about. So this a in front here is going to be my radius that we have. All right? So this is centered at the origin. Is every single circle known to man always centered at the origin? No, right? That is not how life works. So if I am moving around and going somewhere else, this is what that looks like. X naught plus a cosine bt. Y is equal to y naught plus a sine bt. With center x naught, y naught. Right? And my radius is still the absolute value of a. Now let's talk about transformations here for just a second. Think back to that pre-calc, because we just did this in pre-calc this semester is what makes me think of it, or algebra, or whatever in the world you want to talk about. Your transformations, if you're adding or subtracting to that outside of the function, then that is that shifting transformation. I'm taking up my whole graph and I'm moving it to somewhere else. It is a big shift that we have. And here's center radius form. Just like we talked about before, but if we use these same variables, x minus x naught squared, y minus y naught squared is equal to a squared. So that is center radius form for a circle. I have my center and I have my radius, or you can break this up in terms of parametric, and you're using cosine and sine in parametric because sine and cosine are those circular functions, right? Using those circular functions is how you can make those parametric equations work for a circle. All right? Okay. So we're going to do some problems that deal with that. This problem up here is that exact same thing. You could look right here at this problem and you say, all right, bring it, right? Here is my angle measurement. No problem. I know that it is positive, so I'm going to be going in the counterclockwise direction. Nailed it. This is my radius. Got that? No problem. I could have looked at this right off the bat and said, okay, that's going to be my radius, centered at the origin because I'm not adding or subtracting anything else to it. So it's centered at the origin, and that's my radius. So you can take these parametric equations and go right to graphing your circle because you know this generic parametric equations for a circle. All right? That's the connection right there. All right. Circle's not too bad.